All right, in this video we're going to do a couple example problems on cylindrical coordinates. And the first problem, it says evaluate this integral. So it's a triple integral over the solid region E of the function z times dv. So the first thing we're going to need to do is to turn this into an iterated integral. Z times the function, z is the function we're integrating, and then now dv, that becomes r dz dr d theta. That's equal to dv in cylindrical coordinates, the volume element. All right, and then we must have some solid here. So E is enclosed by the paraboloid z equals x squared plus y squared. So okay, so we have this paraboloid z equals x squared plus y squared is going to look something like that. And the plane z equals 16. So there's this plane z equals 16 that's sitting above. Okay, and so the region they must want is sort of this solid bowl-shaped region in there. That's the region we're integrating on. All right, and so we'll start with the z-coordinates. So the z-coordinates start here on the paraboloid below, and they go up until they hit the red plane there. So the z-coordinates should go up to z equals 16, that's the top, and they should start at z equals x squared plus y squared. Well, that's r squared in polar coordinates. So that's my bounds on the z's. And then for the thetas and the r's, what I need to do is I need to think of what is the shadow region in the xy plane that would be that I'm integrating over, and that's going to be a circle, right? So if we look at this intersection here, it's going to intersect in a circle, and when I project that down, we're going to get a circle. And the way I figure out what circle is I just intersect the two things. So I know that z is equal to x squared plus y squared. I also know that z is equal to 16, so that's going to be the circle r squared equals 16 or r equals 4. So r equals 4 would be the circle. And I think I want all of the angles from 0 to 2 pi. So I can take my theta from 0 to 2 pi and the r's from 0 to 4. So now I've got bounds and I've got an integral, and I can just work out what the integral is going to be. So let's see if we can do that here. Integrate 0 to 2 pi, integrate 0 to 4. And then dz, so integral will be r times z squared over 2, evaluated from r squared to 16, dr d theta. And that's going to be 0 to 2 pi, 0 to 4. What is 16 squared divided by 2 is 128. So I'm going to have 128r minus r squared squared, which will be r to the 4th, times r, which makes r to the 5th, over 2 dr d theta. Okay, now I can integrate my r's. So I'm going to get half of 128 is 64r squared minus r to the 6 over 12, evaluated from 0 to 4, d theta. So 64 times 4 squared is 1024, minus 4 raised to the 6th power divided by 12 is 1024 over 3. That would be plugging in 4, and then we get 0 minus 0 when we plug in 0. And now we're going to integrate the thetas, so we're going to get 1024. Well, actually, we could combine these two together. Why don't we do that quick? 0 to 2 pi. So 1024 minus 1024 over 3 gives me 2048 over 3 d theta. And then when I Do the antiderivative, I get 2048 over 3 theta from 0 to 2 pi, which gives me 4096 pi over 3 minus 0, of course, and 4096 pi over 3 is the right answer. Okay, so that's the first problem. Pretty straightforward. Draw the picture, write down the integral, and then do the calculus. All right. The second problem we're going to work out is a similar one, except this is a volume problem. So when they say find the volume, we do a triple integral over the region, the solid region, but we just do the one function. So integrating the one function will give us volume. All right. Now the question will be, what is that region? So we'll need an iterated integral of 1 times r dz dr d theta. That will be cylindrical coordinates now. And to work that out, we're going to need to know what the region is. So it says it's within the cylinder and the sphere. That lies within both the cylinder and the sphere. Okay, so we have some cylinder here. X squared plus y squared equals 16. That would be r squared equals 16. Which would, I guess, be r equals 4 then. So that's the cylinder r equals 4. And we have to be inside that cylinder. And we have to be inside this sphere, which is the sphere of radius 6. So there's going to be some radius 6 sphere. So if we have to be inside that as well, then I think what we want is sort of this kind of funny shaped cylinder with a cap on it region. Okay, so the z coordinates top to bottom look to be coming from the sphere. So that means I'm looking at x squared plus y squared plus z squared equals 36. I can write that as z equals 36 minus r squared square rooted, plus or minus, because x squared plus y squared is r squared. I can subtract that over, solve it for z squared, and then square root both sides. So that's going to be my z's from negative root 36 minus r squared to positive root 36 minus r squared. And then in the xy plane, well, we have this circle, radius 4, and we have all the thetas between 0 and 2 pi. So theta, 0 to 2 pi, r, 0 to 4. Okay? So now we've got ourselves an integral, and we just need to work out what that integral is. Okay, so first we're integrating with respect to z. So I'm going to just kind of make some space here. So this is going to equal 0 to 2 pi, 0 to 4. Integrate the z's, we'll get r times z, evaluated from negative 36 minus r squared to positive 36 minus r squared in the square root, dr d theta. And when I put that in, I'm going to get r root 36 minus r squared minus r root 36 minus r squared dr d theta. But that's, of course, just equal to 2 of those. Sorry, minus a minus, because we're subtracting and there's this minus sign. So that's going to become plus. So there's going to be 2r root 36 minus r squareds dr d theta. Okay, that looks like a integrated from 0 to 4. That looks like a classic u substitution. U equals 36 minus r squared. Du equals 2r dr. Negative. So if I put a negative there and a negative there, now I've got u du. So this is going to equal negative 0 to 2 pi integral the square root of u du. And what do the u's go from? R started at 0, so u starts at 36, and r ended at 4, which is going to go to 20, because 36 minus 4 squared is 20. All right, and then I can do that integral in terms of u now. It's an integral I know how to do. Root u. Root u is u to the 1/2, so I'll have 2/3 u to the 3/2. Evaluated from 36 to 20 du. That now just makes 2/3 of, I guess, 20 to the 3/2 minus 36 to the 3/2 d theta. I missed a d theta up here, sorry. And then I can integrate the thetas. So now I'm going to have negative 2/3 of 20 to the 3/2 power minus, well, I guess 36 to the 3/2 power. I think that's 216, isn't it? Yeah, that's 216. Times theta evaluated from 0 to 2 pi. So this is going to give us negative 4 pi over 3 times 20 to the 3/2 power minus 216. And I think 216 is bigger than 20 to the 3/2 power, which makes the inside negative, and that's negative, so the volume should be positive. And if we check back up, we get, well, do we get that? What are they saying? 4/3 pi, 4/3 pi times 216 minus 40 root 5. If we take 20 to the 3/2, is that what they have? Yes. Okay. So we did get the answer correct, and that's how you do that one. So read the problem, draw the picture, write down the integral, and then after that it's really just calculus until you get the answer. All right, so hopefully those examples are helpful for you, and good luck with your own problems involving cylindrical coordinates.